Let's spend a couple minutes reviewing the optics of the diamond that we talked about on Friday. Remember, on Friday we talked about the 4 C's of diamonds. One is the clarity, how clear it is versus fogginess, right? We want it clear. The color, we usually want it no color. Okay, the carats, the size of the diamond is pretty important, obviously, but arguably the most important thing is the cut of the diamond. If we have a ray of light coming into this diamond, it's likely coming into the diamond from above. So let's draw this ray of light coming into the diamond from above. When it hits that boundary between the air and the diamond, it's going to slow down quite dramatically. In fact, it's going to slow down, but it's not going to change direction, and that's because it's going straight in. It's going in at an angle of 0 degrees. You can't change direction when you're going in at 0 degrees. Throw a rock in water at an angle, it'll change direction. Throw a rock in water straight down, it keeps going straight down, even though it does change speed as a result of that. So this ray of light hits this boundary right here. Now, there's a relatively small angle that you see there, an angle of incidence. But diamond has a really, really high index of refraction. And because it has a high index of refraction, it has a low critical angle. So the chances of this being bigger than the critical angle are actually pretty good. Okay, the angle at which total internal reflection begins to occur. Okay, it's pretty good at being above that. All right, we reflected off the surface there, assuming we're above the critical angle, such that the angle of incidence equals the angle of reflection. Now it hits the boundary between the diamond and the air on the other side. If we look at that, it looks like the angle of incidence is about the same as it was over on the left side. So what's going to happen if it reflected on the left side? It's going to reflect again, up like this, back out the top. We see a little sparkle right here. We see a little sparkle right here. So every time the light goes into this diamond, you're going to see a couple little sparkles. Right? Obviously, you got few thousand rays of light going into the diamond, you're going to see a few thousand sparkles. What happens if we change the index of refraction, make it glass? Well, the critical angle becomes much, much bigger. You can have the exact same setup here, right here with glass, but all of a sudden, that initial angle is not bigger than the critical angle. So what happens to it? Speeds up, goes out the other side with a bigger angle of refraction than it had for an angle of incidence, but it's still refracting. We still don't see that sparkle. Does that make sense? That's if it's not diamond. What if it is diamond? What if it is diamond, but we change the shape of it a little bit? Okay, you're this new young whippersnapper diamond cutter. You think, hey, I'm going to change this around a little bit. It's been done the same way for hundreds of years, but we're going to change things around a little bit. We're going to make these diamonds better. We're going to make the diamond look like this. Same basic shape, but let's make it a little longer. Okay, a little longer and skinnier here. What happens to the light? Well, the ray of light comes in like this, straight in, right? Hits this boundary right here. Looks like we got a pretty big angle of incidence right there, right? We do. Okay, if it was bigger than the critical angle in this picture, it's certainly going to be bigger than the critical angle in this picture. So it's going to reflect. It's going to reflect something like this. Well, now we've got a ray of light striking the surface of the boundary between the diamond and the air over on this side. Well, we've got a completely different angle now, right? It's set up completely differently, so it's going to strike it at a completely different angle. This could still be bigger than the critical angle, but there's less chance of it being bigger than the critical angle. There's a very good chance, in fact, that it's smaller, which means it's going to go out the other side. Okay, we got a diamond. It's cut poorly. What happens? Well, we still see a sparkle, but we only see one of them. Instead of 2 sparkles, we see one of them. What if we change it the other way? You do this and you say, oh, wait a sec, this doesn't look as good. Let me change the shape of it the other way. Let's make it, instead of long and skinny, let's make it kind of short and fat, like something like that. Let's say we got a ray of light coming in here. Now what happens? Well, we could be bigger than the critical angle here still. Okay, if it is bigger than the critical angle, what's going to happen? It's going to go like here somewhere, right? And it's going to go pretty much straight out there because it's striking this surface. It's striking this surface at a really small angle, an angle that's smaller than the critical angle. Does that make sense? So you got diamond. You're probably going to see some sparkling no matter how it's cut. But the better it's cut, the more sparkles you're going to see, which is obviously what we want, right? Make sense? Well, how do we find the critical angle for diamond or for any other material for that matter? What's the critical angle for the quartz glass air interface? Well, let's draw a picture here, okay? We know that when we're finding a critical angle, when we get total internal reflection, we have to be going from an index of refraction that is what to what? From high to low or low to high? It's got to be high to low. If you're going from low to high, let's go from low to high for a second, okay? This isn't going to work. Let's show you why it doesn't work. If you're going from low to high, the light's going to slow down. As the light slows down, as the speed decreases, then the angle is going to decrease as well. We're never going to get an angle of refraction that's greater than the angle of incidence. And in order to get total internal reflection taking place, the angle of refraction must be bigger than the angle of incidence. So, can't go from low to high, it's got to go from high to low. So it's going to look something like this. We're going from quartz glass that has an index of refraction of 1.47 to air that has an index of refraction of 1.00. Here's my angle of incidence. The angle of incidence at which total internal reflection begins to occur. In other words, it's not really reflecting, but it's not really refracting either. Okay, it's that boundary, the cusp at which it begins to occur. When that happens, the angle of refraction will be 90 degrees. When theta I, theta 1, is the critical angle, then theta 2 will be 90 degrees. Let's set that up now. Sine theta 1 over sine theta 2 equals N2 over N1. We're going to change sine theta 1 to sine theta C, the critical angle, over sine 90. Make sense? Equals N2 over N1. N2 will be 1.00, N1 will be 1.47. What's sine 90? 1. In fact, if you want to, you don't even have to write that in. Because when you're solving for the critical angle, that bottom number is always 1. Always. Let's solve for theta c here. It's the inverse sine of 1 over 1.47. I think when we do that, we end up getting, I think, 42.8 degrees. Anybody have that? 42.9 degrees. Everybody do this right now, please, on your calculators. Let's pretend that you got these mixed up. Sine theta is equal to 1.47 over 1. You mixed up the order of them. Everybody hit on your calculators right now. Inverse sine of 1.47 over 1. Let's see what you get. Caden, what do we get? Error. When you're doing a Snell's law problem, you got to be careful to get theta. You get theta 1, theta 2, n1, n2, and all that stuff. You got to be careful to get them correct, because if you make a mistake on it, your calculator is not going to tell you the difference. But when you're dealing with a specific problem involving total internal reflection, if you mess up on which one's the first medium, which one's the second medium, we don't want you to do that because it takes up time, right? When you mess up. But if you mess up, at least your calculator is going to tell you that you've messed up. Seriously, it's hard to get these questions wrong. It's hard to get them wrong. You almost have to work at it to get them wrong. It's easy to get it wrong the first time, but when your calculator tells you you've done it wrong, do it again. Flip over N1 and N2 and see what you get then. All right? Make sense? Let's try those 3 questions, please, for the next few minutes. As we're waiting for the last couple people to finish up these questions, just a couple quick kind of understanding questions for us, not mathematical. I think we're okay with this probably. They're all the same, right? Except that we're dealing with different numbers here. What did you notice about the relative critical angles? The critical angle from A to B to C. We see the answers up in front of us there right now. Water and air produce the biggest critical angle. Diamond and air produce the smallest critical angle. When do you think you get a big critical angle? When do you think you get a small critical angle? Yep. Good. When the difference between the small and the n values is small, okay, they're really close together, we get a big critical angle. In other words, when you've got 2 materials that are real similar to each other, it's difficult to get reflection taking place. When you get 2 materials that are a lot different from each other, with a big difference in the index of refraction, then we get a smaller critical angle. Here's the way that I remember that. Okay, I got a terrible memory for things like that, so I've always got to have a way of remembering it. I look to air and diamond. Okay, air and diamond gives us a small critical angle. Well, how do I know that? Because diamonds sparkle a lot because of that low critical angle. Right? It's easy to exceed a low critical angle. So diamond and air produces a small critical angle. Why? Well, because there's a really big difference in the index of refraction between the two, right? Now, I can go to another material. Let's say demonstration we did the other day in class with the Pyrex and the baby oil. The difference in the index of refraction there was virtually nothing. It was almost identical indices of refraction. How easy would it be to get total internal reflection taking place there? Not easy at all, right? When you've got two materials that have the same or real close to the same index of refraction, we get a really, really big critical angle, which means you're probably not ever going to exceed that critical angle and get total internal reflection. Okay. Your homework for tonight on this topic and on just general refraction problems is going to be worksheet number 17. Okay, so the first number of questions, 2 pages, I think. Somewhere around the first page is just basically basic refraction problems with Snell's law, and then the second page will be total internal reflection questions. All right.